Thank you all for being here. Thank you to Microsoft Research for organizing this very inspiring meeting and for challenging us to think about the future of computing in the 21st century. Now, today, I would like to talk to you about how computation is progressively becoming much more interactive with the physical world and also with people. The next generation of computers will be able to sense the world, they will be able to act autonomously in the world, and they will be able to interact with people. In other words, they will be robots. And I know this because the previous speaker told me so. In fact, John Hopcroft was my teacher and my advisor when I was a graduate student. John, thank you for giving me the opportunity to work on robots with you at Cornell and for opening this great world of excitement to me. So we have come a long way since the Czech playwright Karel Čapek introduced the word robot to denote hard and repetitive labor. Now, some of us fear the idea of machines doing our work, and others are wildly excited by it. But our dream to create machines in our own image that are smart and obedient goes back to antiquity. The quest for smart machines has progressed from the technological marvels of antiquity to the 17th century automata, to science fiction robots, and to today's reality. And they are becoming increasingly more lifelike. Robots today are impacting all aspects of life, from small and near, for example, in medicine, to large and far, for example, in exploring the universe, from manufacturing to homes. Robots contribute to science and knowledge and make the world a better place. Now, in order to build robots, we really need a broad spectrum of technologies. We need sensing, we need the ability to interact with the world, we need decision-making, we need human-machine interaction, and we need the supporting software and hardware to do so. But robots are becoming ever more autonomous and capable. And imagine, in this reality of robots, I would like to start with one example. So imagine all the tasks in your home that you would like to automate. Maybe you would like to have a robot to fold your laundry. Maybe you want to have a robot organize your rooms. Maybe you would like to have a robot cook your meals in the kitchen. Well, it turns out in the kitchen, we already have some small robots. So we have a robot that washes our dishes. We have a robot that cooks things with science. But there's still a gap between these existing robots and something we would like to call the Iron Chef robot. So what is the problem? Well, if you think about all the things you've got in our kitchen, we have cabinets that are challenging to open. Inside the cabinets, there are a huge variety of packages and things. We have dials on our stove for cooking. And we have objects in the kitchen that are really, in general, very hard to model and unpredictable. So how can we bridge the gap between this complexity in the kitchen and actually putting a robot chef that will make food for you? Well, one thing we can do is we can bring all the ingredients. We can simplify by putting them on the counters. And this mise en place is, in fact, what the Iron Chef is faced with on our TV shows. We can use standard tools, and we can model a human-centric workspace. So my students, in fact, my undergraduate students, who are just like you, have been taking the challenge of making this robot chef, and have been developing a system called BakeBot. I would like to introduce to you. Now, this robot executes simple baking recipes from mise en place setups until the robot actually generates finished products, like cookies. Cookies tend to be very popular in our laboratory. The robot uses a human-centric workplace, but it uses standard tools. In other words, the robot uses spatula to mix objects. And starting from a generic recipe given to the robot in natural language, the robot is able to execute a sequence of instructions that enables it to go from basic raw ingredients to finished products, to cookies. So let's watch this movie for a while. We have created a database of recipes supplied in natural language, and on the video screen you see what these recipes look like. And we have developed a natural language parser that takes these recipes and breaks them down into actions that can be executed by the robot. We have then implemented new control strategies that enable the robots to do things like mixing, scraping, finding objects, pouring. And in this video, you see BakeBot execute some of these instructions that were automatically generated from a recipe to make Afghan cookies. So I introduced to you our robot, Mans and Manos, which means mind and machines. It turns out mixing is actually much harder than you'd think, especially for machines. But this can be done using state-of-the-art perception algorithms and state-of-the-art manipulation and planning algorithms that enable the robot to find the next ingredient needed in the recipe, pick up the bowl, add the ingredient to the bowl, and then mix to blend everything in. So Afghan recipes are, Afghan cookies are chocolate cookies that have crunchy cereal in them. And so here's our robot successfully having read the instructions and mixed the batter. Now, the robot is not the most graceful executor in the kitchen, but nevertheless, it successfully executed the mixing, and it created the batter. The robot is also very efficient because now it's noticed that there is a little bit left in the bowl, and it will go ahead to scrape it. So our robot chef is also able to find the oven in the kitchen and open the door. And the robot uses wheels for moving back and forth between different workstations. And here's the robot going back to the mixing workstation and bringing the cookies to the oven. So let's see. The 20 minutes of baking time is the required baking for interval for this recipe. And after 20 minutes, here is the result. And this is my student Mario who developed this recipe. So I encourage all of you to bring robots in your laboratories, because then you will have the pleasure of having fresh cookies baked by the robot every day. So it turns out that there are other tasks inside the home and in the world that you might want to automate. And some tasks require more than one robot. So for instance, say you are moving to a new room or new apartment and you want to buy new furniture. This is an example where a group of robots are able to work together and cooperate to assemble your next IKEA set of furniture for your rooms. So in this case, we have two robots equipped with robot arms. These are laboratory replicas of industrial robots. And these robots have specialized tooling that is added to their grippers to enable operations that are actually very complicated to execute by robots, such as screwing. Here you can see a close-up of how the robot finds the parts and mates them, and the mechanism used to spin the part in place. And by the way, this work was done by undergraduate students in my laboratory, and it's been a very exciting project. So, with these examples, I would like to show you that, in fact, in order to create autonomous systems that will do things for you, it's important to think about multiple robots working together, especially when you have a large-scale environment or a complex environment, like in the case of the furniture assembly robot. So in this environment, the robots move around to sense the environment. They compute based on the values they sense from the environment, and then they take some action. In the process of sensing, each robot will aggregate information that is only local to the robot, and this information may be valuable to the other members of the team. So communication is an important aspect of these kinds of machines. And because of that, we have a distributed system in which each robot has access only to local information, but what we would like is to guarantee some sort of global behavior for the system. In other words, make sure that your team of robot furniture assemblers will assemble the correct bed or table for you. So with these examples, I would like to tell you three things. So I would like to tell you that in order to make these amazingly capable autonomous systems, we really need to know mathematics. We really need to start by modeling these systems and by building a theory on how they work. The next step you need is you need to know how to program. You need to be able to implement these systems in hardware and in software. And the third thing you need is you need the courage to follow your dreams. So you really need to be able to think about what kind of new capabilities or activities you would like to enable the systems you are creating to do. And just go for that. Go for your dreams, because it's possible to implement them. So let me say a few words about each of these three important things. So with theory and algorithms, I just want to give you an example of the flavor of the kind of theory you need to develop that allows you to model robots that think locally, yet have a guaranteed global behavior. So the problem I would like to use for this is a very simple example. I have an environment, I have a bunch of yellow robots that can sense in the environment, and I want to place these robots in a way that matches how interesting the environment is. So in other words, where it's interesting, I want to collect a lot of samples, and where it's less interesting, I want to have sparser sensing. And in order to solve this problem, I actually have to think about a number of different aspects of computer science. So I have to model the multi-agent dynamics, and this comes from a discipline called control theory. Then I have to model how the robots communicate with each other, and this can be done by using graph theory. And finally, I need to think about how the robots sense, and this comes from learning and estimation theory. By bringing these mathematical formalisms together, we can actually come up with algorithms to solve this problem. So it turns out there is some very specific mathematics that enables us to formulate this problem in terms of a strategy that involves gradient descent, in terms of a strategy that involves computing a cost function, doing some local sensing and analysis, and moving according to what this cost function tells us to do. And maybe the mathematics is not so important for this talk, but the general process is, if you do not know where the environment is interesting, then you would like to actually learn that. So you would like to learn the weighting function that goes with the cost function in the system. You'd like to then use it to estimate the next place where the robots have to move, and then actually act by moving. So using mathematics, we can come up with a formalism that shows us how to drive the robots in such a way that their motion will optimize a cost function representing the collective cost of this network. So an interesting technical aspect of this is, how do you learn where it's interesting in the environment? And the way you can do that is by approximating a function that tells us how the environment is interesting using something called a basis function. So basis functions can be anything. can be Gaussians, they can be wavelets, they can be polynomials. And in general, they have these unknown weights in front of them. And these unknown weights can be learned by doing measurements in the environment. So the idea is like this. The robots have some estimate of what the sensory function looks like. They take a measurement. They get a sense of how far off their local estimate is from what they have just measured, and they correct the parameters. In other words, what is needed for a good solution is an algorithm that enables the robots to move in the physical space to cover the environment while learning the parameters of this of the sensory function in a parameter space. And it turns out that if every robot does this locally, the whole system will converge in a guaranteed way to robot configurations that are guaranteed to match where it's interesting in the environment. So this is pretty amazing. If you think about launching a group of robots in a place you don't know anything about, doing very small local operations, and then ending up with something that is absolutely guaranteed to be the solution of this hard problem, it's very, very amazing. And this is what we get from being able to apply mathematics to model the problem. So here's the practical control algorithm that results from this. Each robot measures some coordinates, computes a geometrical object, measures a sensory function, updates parameters, and then applies a control input. And that's all there is to it. So here's a little simulation that shows a group of robots, and if you look carefully, there are 2 red crosses in this environment, and these red crosses are where it's interesting in the environment. And you can see in the 3 graphs, you can see the point of view of each robot as it runs in the world, trying to estimate and approximate the location of these important events in the world. So I wanted to give you a sense of how mathematics can be used to encode a very hard problem in a practical way. But what can we do with this in a really practical situation? So consider instantiating this solution to a very simple problem. Now my robots can fly, and they have downward pointing cameras. And I would like for my robots to spread out in the world in such a way that their camera covers the entire environment, so that they can perhaps do continuous monitoring of the environment. Well, using the same methodology of gradient descent using a cost function, we can instantiate this problem by introducing a cost function that has a lateral component to drive robots to move inside the region of interest and away from neighbors, in other words, to spread out, and a vertical component that allows the robots to move down to see better while moving up to see more. So the critical thing is coming up with a trade-off between all these 4 components. And it turns out that this is sufficient to implement a very sophisticated algorithm where we do not have to know ahead of time how many robots are in the system. And the robots will adaptively collect samples in the world, figure out how to move to optimize this cost function, and place themselves at optimal locations that will give us the coverage of the environment according to the highest possible resolution. And to show you that the system is independent on the number of robots, here is Brian, the father of the system, killing one of the robots. And here are the robots readjusting to make up for the failure of this 3rd robot. And in fact, the 2nd robot dies next, and you will see the remaining robots shoot way up, because that will enable the camera field of view to cover more of the space. So, okay, this is a laboratory experiment that shows you how you can take a practical theory and implement it on real hardware. What can you do with it? So one possible application is in biology, where biologists sometimes like to find invasive tree species. So in this picture, you see some trees that are much darker green than the others. And those are invasive trees brought on an island in the Pacific. And these trees are removing all the nutrients for the native trees. They should be eliminated. But it's impossible to tell where these trees are from the ground. However, if you bring a fleet of robots and you allow them to hover above the tree canopy, you can aggregate mosaics of images like this one. They will tell the biologists exactly where the bad trees are. And then the trees can be eliminated. The other thing you can do is you can use these robots to get a glimpse